Good day, everyone. Uh, Today we will move on to the next topic, which is on mixing processes. Compared to the previous topic, this is quite shorter. And before we start, I would like to acknowledge Ma'am Rowie for the slides. And also before we begin, I would like to clarify a few things related to the previous lecture. I mentioned there that both ideal gas model and ideal solution model have simplifying assumptions. So they are similar in a way that they have simplifying assumptions, but the specific assumptions for the two models are different. Okay, they are similar, they have because they have simplifying assumptions, but the specific assumptions is different for the two models. So I leave it up to you to research or recall what are the assumptions under ideal gas model and what are the assumptions under ideal solutions model. Okay, so let's begin by uh, reading the learning objectives. First, define in words and equations standard property changes of mixing. So remember we're under the new topic mixing processes. Compute excess properties and partial excess properties corresponding to property changes of mixing. So we're still going to talk about excess properties, which we have dealt with in the previous lecture under solution thermodynamics. Interpret and apply enthalpy concentration diagrams, understand conventions for tabulating heats of solutions, and use them to compute heat effects and uh, mixing and dissolution processes. So, again, the question is, why is mixing process important in thermodynamics? So first, of course, I'm sure you know what mixing process is. It's the process of mixing two or more different substances or systems, and it is crucial in understanding the behavior of mixtures and their thermodynamic properties. So this topic is crucial for that. But why is it important? It's because it has various applications, such as in chemical reactions, phase equilibria, separation processes. So it's important um, to study mixing processes in order to understand the mentioned applications. Okay, so moving on. First, let's discuss the property changes of mixing. So in a standard mixing process, one in which there's an appropriate amount of pure chemical species at a temperature and pressure are mixed to yield a uniform mixture. Okay, so the mixture is uniform of specified composition. So the mixture has a specific composition at a certain temperature and pressure. And the pure species are said to be in standard states because we're talking about the standard mixing process wherein the pure species are in their standard states and their properties are the pure species properties V sub I. So um, remember V sub I is the pure species property of species I for volume and H, SI, etc. Okay. So let's represent the standard mixing process in this diagram and let's try to observe what happens when there's mixing. Okay, so if for example we have an experiment wherein initially so there's a cylinder right here. Initially there's a partition that separates species 1 with species 2. N1 represents the number of moles of species 1 and N sub 2 represents the number of moles of species 2. They are both at a certain temperature and pressure. There's a cylinder right here that um, closes the compartment. Okay, so therefore there's an applied pressure right here. And then as I've mentioned, initially there's a partition that separates the two species. So what is uh what possible phenomenon happens when we try to remove the partition. There's either expansion or contraction, and this is reflected by the movement of the piston. So if, for example, it expands, then the piston moves to the right, and if it contracts, then the piston moves to the left. Okay? And then another thing that happens is there's temperature change. Okay, so there's and this is reflected by heat transfer to restore temperature T. That's why there is Q here. Okay, so that is that is what happens when there is mixing. So there's volume change and temperature change. So if we want to represent the change in volume, uh, we can designate that as delta V superscript T. Okay, the final volume, which is uh, V, okay, this is the final volume multiplied by the total number of moles. So wherein V is the specific volume. That's the final volume minus the initial volumes of the two compartments, V1 and V2, multiplied by the respective number of moles. So this would give us the delta V of mixing. We divide everything by the total number of moles, N1 plus N2, and we get this equation. Now in terms on the right hand side of the equation is now in terms of X, which is the composition. Okay, so that is the equation for the volume change of mixing. How about the other phenomenon that we observe, which is the temperature change? So the enthalpy change of mixing at constant pressure, or we also call that heat of mixing, okay, is equal to Q, and that is equal to the change in enthalpy. So this would represent the change in enthalpy of mixing, or the heat of mixing. Again, it's the final enthalpy multiplied by the combined number of moles minus the initial enthalpies of each of the species multiplied by their number of moles. Okay, so this gives us the delta H of mixing, or delta H superscript T. Dividing everything again by N1 plus N2, the total number of moles. Now we have an equation represented by the composition. So we can make a general, based from these two equations, we can make a general equation. So for any property, delta M is just equal to the um, property of the mixture, right? Minus the summation of the initial properties of the individual species. The way that we uh, derive these equations right here. So it's just that we generalize the equation into M for any property. So this is the property of the mixture minus the summation of the composition, or mole fraction of the individual species multiplied by the property of the individual species. All right. Um, so we can write this for the other properties, and entropy and gives free energy. Okay. But what do we notice right here? What is this form? Uh, it looks like the excess, okay, right? The excess property. If you will remember, let me go to that slide from the previous lecture. Okay, so this is that slide. Our uh, equation for the excess property is uh, M minus M ideal. And M ideal, if we will go back to uh, the previous table, it's just represented by the summation of the mole fraction multiplied by the property of the species. Okay, so therefore, for volume and enthalpy, the change of mixing are equal to the excess property. Okay, I hope that is clear. And also, the property changes of mixing are functions of temperature, pressure, and composition, and are directly related to the excess properties. Right? For ideal solution, each excess property is zero. So, as I mentioned in the last lecture, for an ideal solution, uh, excess property has no meaning. And what do you notice? Okay, um, excess excess and mixing are it's the same. Okay, the same for volume and enthalpy, but it's not different. I mean, it's different for entropy and gives free energy. Okay, so the reason is that aside from being a function of temperature and pressure, for entropy and gives free energy, just like our reasoning before, it's also this term right here makes it a function of composition, which is due to the uh, entropy increase due to random mixing. Okay, it is important to take note that if we're dealing with an ideal solution, so this would be transformed to VID. It's equal to zero. Each excess property is zero. And also, um, for SID and G superscript ID, we will be left with the second term only. So let me uh, refer you to the book right now. So this is a special case for an ideal solution. Each excess property is zero. All right. And then let's look at next the excess enthalpies for an example system, which is a binary system of ethanol and water as a function of composition. So on your y-axis, you have the excess enthalpy, uh, which is joules per mole, and then on your x-axis, you have the composition in terms of the mole fraction of ethanol. So we have different isotherms ranging from 30 to 110. And what do we notice? For the lower temperatures, the curve lies below the x-axis, which means it's negative. So therefore, for lower temperatures, the behavior is exothermic. Exothermic, there's a heat removal required for isothermal mixing. So in order to maintain the temperature, heat is removed. But for higher temperatures like 110, the curves lie above the x-axis, which means the values are positive, and it means it's endothermic, and it means that heat is required, or heat addition is required for isothermal mixing. But for intermediate or middle temperatures, they lie both on the exothermic and endothermic regions. So we can represent these curves by a polynomial equation in as a function of mole fraction. And we have to multiply it by the product of x1 and x2 to ensure that the excess properties goes to zero at both ends, meaning it goes to zero for both pure components. And also written on the slide, as you can see, we have a general equation for the partial excess property. Uh, it looks familiar because it's somehow looks like our previous equation in the previous lecture for partial property. Let me go back to that. This is the previous lecture on solution thermodynamics for binary systems, the partial property for species 1 and species 2. So um, this one now deals with the excess partial property. Okay. Next, we discuss the common features of the composition dependence of the change in Gibbs free energy, change in enthalpy, and T multiplied by the change in entropy. Okay, so the the graph right here on the left shows the uh, properties delta G, delta HT, delta S of different of 6 binary liquid systems. Okay, the text is quite small, but these are different systems, and as you can see, the behavior is different for different systems. But despite that, they have common features. Number one, each change in property is zero for a pure species. And as you can see, for delta G, delta H, and T delta S, they go to zero at both ends of the graph. So that means for pure species, the change in property is zero. So that is true for all graphs, regardless of the type of binary system or the species in the binary system. Next, the Gibbs energy change of mixing, delta G, is always negative. Okay, so as you can see here, let me zoom right here. Delta G is always or lying on the region below the x-axis, which is the negative region. So that is always true regardless of that um, binary liquid system. Okay, and what does it mean? So when we have a negative delta G, it implies spontaneity. So for a mixing process to occur, then um, delta G that is negative means that it's spontaneous. And that is because it's a requirement that the final Gibbs energy be minimum, okay, for an equilibrium state at specified T and P. Okay. And finally, the entropy change of mixing is always positive. And that also means that uh, when we mix species in a system, that means the entropy increases. There's a positive entropy increase, reflection of second law of thermodynamics, and which means when we mix two or more species, right, then the randomness of the system increases, right, which is true, right, when we do mixing. All right, so that is the graph for the delta G, delta H, and T delta S. And just a note again, which we discussed before, um, excess and mixing changes are the same for enthalpy and volume. Okay, the next slide is an example for heat of mixing. So I will now open the whiteboard. Okay. So first, let's read the problem. The heat of mixing for liquid species 1 and 2 at fixed temperature and pressure are measured calorimetrically and is represented in some appropriate units by the equation delta H equal to x sub 1, x sub 2, quantity 40, x sub 1 plus 20, x sub 2. Determine the expressions for the partial molar excess H for species 1 and the um, H excess enthalpy of species 1 as a function of x sub 1. So what do you notice about this equation? It's multiplied by the product of x sub 1 and x sub 2, which is um, how we write the curves for delta H to ensure that the curves will go to 0 at both ends of the graph, which represents the pure species 1 and 2. Right. So all right, let me pause for a while to look for my pen. Let's begin by writing the given. Okay, given, so we're given the equation delta H equal to x sub 1, x sub 2 multiplied by 40 x sub 1 plus 20 x sub 2. Okay, and the required would be expressions for H1E. Oops, what happened? Expressions for H sub 1E partial molar. Okay, wait lang. H sub 1E and H sub 1 E. So the excess partial molar and the partial molar enthalpy as a function of the composition. Okay. So for the solution, what do we need to do? There's a clue. It's a function of x sub 1. So since the equation is a function of x sub 1 and x sub 2, we simply remove x sub 2 first from the equation because we know that x sub 2 is 1 minus x sub 1. So we replace that from the equation by x sub 1, 1 minus x sub 1 multiplied by 40 x sub 1 plus 20 1 minus x sub 1. Okay. And then we expand the polynomial. So I will just skip the intermediate part and leave you up to it minus 20 x sub 1 squared minus 40 x sub 1 cubed minus 20 x sub 1 squared plus 20 x sub 1 cubed. There are terms that would cancel out, like, okay, hold on, minus this one, so this one, ah, Alright, so I made a mistake somewhere and I resolved the problem. So now we can cancel this one. Uh, and we are left with delta H equal to 20 x sub 1. Alright. Okay, this one should cancel out, not the other one. So 20 x sub 1 minus 20 x sub 1 cube. Okay. Uh, alright, so we have delta H in terms of uh x sub 1 only. We managed to remove x sub 2. How can we get the partial molar re- excess properties? I mean, equation. Okay, let's go back to the slide. Okay, we're showing the slide right now. Here, right here. So we need these equations to get the partial molar excess property. So let's simply copy that to our whiteboard. Okay, let me copy that. DHE. So in terms, I will express it in terms of enthalpy is equal to HE plus X2 DHE over dx1. Okay, so what do we need? We need an expression for HE and um, DHE with respect to dx1. I would so if you will remember from our previous slides, the excess enthalpy is just the same for the change delta H of mixing. Okay, let me again go back to the slide. Okay, right here. So we can simply just replace delta H with H excess. Okay, so let's go back to the whiteboard. Uh, so here we can equate that to HE. Okay, so we have HE. So we need an expression DHE over dx1. So we derive this in terms of x1, I mean with respect to x1. So that's simply 20 minus x1 minus 60 x1 squared. Next, we substitute everything back to the equation, the partial molar equation. Okay, so let's do that. H1 E is equal to HE, which is 20x1 minus 20x1 cubed plus x2. Okay, so now we want to remove x2, so just replace that with x1, 1 minus x1. Okay, so again, I'm uh, substituting the equations back into this partial molar excess H equation. And now I multiply it with dHE over dx1, which is 20 minus 60 x1 squared. Okay. Expanding and simplifying, I leave it up to you to do the intermediate steps. Our final equation is 1 squared plus 40x1 cube. Okay? So this is our answer for uh, the first requirement. Okay? What's happening? Okay. Next, we're being asked for h1e as a function of x sub 1. Then that is simply, okay, the first equation, uh, okay, so I think there's a typo in the problem. So this second one should be H2 sub E, partial, okay, partial molar H2 sub E. Okay, I'll ask Ma'am Rowie, but for now, let's calculate for H2 sub E. So we use this one, equation 2, and do the same. Okay, repeat the procedure. I will not anymore show the details. Okay, but use the equation H2E equal to HE minus x sub 1 dHE over dx1. Okay, and again doing the same procedure and simplifying, you will get an equation for the partial molar excess enthalpy for species 2, which is 40 x sub 1 cube. Okay. All right. So this is the solution for example 1. Let's stop the video first, okay, and just proceed in the next video.